Part 2 of our discussion of near-number arithmetic will deal with the operations of multiplication and division. Again, a remark is in order. Formally, division is defined as multiplication by a reciprocal. We don't always think of division this way, but again in the context of near numbers, we'll find it advantageous to do so, because multiplication is simply easier to think about, and we've already said all that we have to say about reciprocation during the video on functions in near numbers. Multiplication operates similarly to addition, except that now we're multiplying, and we now have to be careful with infinities and near zero. Let's start by focusing on non-negative factors, which is a bit simpler because multiplying by a negative number reverses inequalities. Multiplication of finite near numbers squeezing towards positive values works very similarly to what we saw for addition. We just multiply the bases and use the very same rule for the adornment. For example, we could take 2 plus times 3 minus. Here are the slices of our two factors. If we take numbers toward the left of these slices, we'll get products to the left of 6. If we take numbers toward the right of these slices, we'll get products toward the right of 6. And we get everything in between. As pictured, we get the open interval from 5 to 7.5. Now let the near numbers squeeze. We see something that fits into 6 plus minus dot. We can do similarly for any other pair of basic finite near numbers with positive bases to see what happens, so it's not essential to memorize the rule. What about the product of positive infinity with a basic finite near number squeezing toward a positive base? Let's try 0.01 plus minus dot times positive infinity. Here are slices of the two factors. Let's make our life easier by squeezing them a bit in advance, which we can always do. Let's squeeze them until the 0.01 plus minus dot stays away from 0. If we squeeze enough, the picture for any basic finite near number with a positive base will eventually look something like this. What products will we get from these two slices? Well, the first factor will be greater than 0.005, and the second factor will be greater than 100. So the results will all be greater than 1/2. In fact, the product slice will contain all numbers greater than 1/2. Now what happens when we squeeze? The numbers in the first factor squeeze closer and closer to 0.01, but those in the second factor push larger and larger, and the products thus push larger and larger. I think we recognize this behavior. The result fits into positive infinity. This demonstrates the rule for the product of positive infinity and any basic finite near number with a positive base. One more easy one, which is easy to guess. Positive infinity times positive infinity. Here are the slices of the factors. Multiplying all numbers greater than 1 by all numbers greater than 1 yields all numbers greater than 1 times 1. As the factors squeeze, the products squeeze even faster, and we see that our result fits into positive infinity again. That's not so surprising. Positive infinity times positive infinity yields positive infinity. Is anything enough to defeat positive infinity in a product? We all learned in school that 0 times anything is 0, but were we lied to? Let's see about 0 times positive infinity. Here are slices of the two factors. Now what happens when we find all possible products? Well, the first factor is always exactly 0, so the product of it with every number in the slice of positive infinity, no matter how large, is simply 0. It doesn't matter how far positive infinity squeezes. We see that our result sits still at 0 dot. It looks like we weren't lied to. The number 0 times anything, including infinity, is simply 0. Phew. Finally, we come to the other special positive near number for multiplication. 0 plus, which is most definitely not the same thing as the number 0. Let's look very carefully at 0 plus times 100 plus minus dot. Here are slices of the two factors. How small of products could we get? We'll have arbitrarily small positive numbers, times 100 say, which still give arbitrarily small positive numbers. How large of products could we get? Well, we've got numbers up to 1/2 in the first slice, times numbers up to 100.5 in the second slice, which gets us up to a little more than 50. Now let's let the factors squeeze. Our first factors are getting smaller and smaller, while the second factor is just squeezing towards 100, so the product squeezed closer and closer to 0. Our result fits into 0 plus, and the number 100 and its adornment were inconsequential. It doesn't take much thought to see that 0 plus times 0 plus fits into 0 plus. We're multiplying smaller and smaller positive numbers by smaller and smaller positive numbers, which definitely yields smaller and smaller products. A quick recap. Suppose we have a basic finite near number squeezing towards a positive base. If we multiply it by positive infinity, we get positive infinity, and the positive infinity wins. If we multiply it by 0 plus, we get 0 plus, and the 0 plus wins. It appears that positive infinity and 0 plus are the big winners for multiplication, just as positive infinity and negative infinity were for addition. We'll note why this isn't surprising in the third video of this lesson. So what happens when we multiply 0 plus times positive infinity? Remember, this isn't the number 0 anymore. Here are slices of 0 plus and positive infinity. The smallest products we could get would be multiplying arbitrarily small positive numbers by, say, 2, which give us arbitrarily small results. The largest products we could get would be multiplying, say, 0.4 times arbitrarily large positive numbers, which would give us arbitrarily large results. We can also get anything in between. So our set of products consists of all positive real numbers. What happens to the results when the factors squeeze? Absolutely nothing. We can still get as small of a product as we like, and also as large of a product as we like, and everything in between. So we've seen that 0 plus times positive infinity is equivalent to the constant interval 0 infinity. And fitting into this isn't much better than fitting into star, so this is another star form. Again, to be clear, 0 plus times positive infinity is equivalent to the constant interval 0 infinity, and both diverge. But a statement that alpha fits into 0 plus times infinity is indeterminate for alpha, as it doesn't tell us enough to determine whether alpha converges or not. Transitioning to products including negative factors, we also get star forms independent of what the signs were here. Any combination of plus, minus, and/or plus minus gives us another star form for multiplication. That's all we have to say about products of positive factors. If one or both of our factors is negative, things get just a bit more complicated with multiplication because of the fact that multiplying by a negative flips things around. We can still think them through from scratch, but if we want to be very careful in a computation, the easiest thing to do is factor out negatives first so that we can think through a product with positive bases. For example, let's look at the product of 2 plus and negative 4 minus. Factoring a minus sign out of negative 4 minus, it changes to the negative of 4 plus. Pulling that minus sign all the way out, we just need to find 2 plus times 4 plus, which is a nice product with positive bases and comes out to 8 plus. Putting the negative back in, we have a result of negative 8 minus. We won't always have to be that careful with the adornments. When they don't matter, we're free to say that 2 plus times negative 4 minus certainly squeezes closer and closer to negative 8 in some way, and just write that it fits into negative 8 plus minus dot. This is still correct, but not as specific as we could be. We do need to be prepared to work carefully in situations where the distinction does matter. The near number 0 plus minus has both positive and negative parts no matter how far we squeeze, but it can be considered one piece at a time as the union of 0 plus and 0 minus. Fortunately, these are easy to multiply individually by basic finite near numbers and yield star forms when multiplied by a basic infinite near number. For example, let's look at 0 plus minus times 0 plus minus. Working one bit at a time, we have 0 plus times 0 plus, which gives a 0 plus, 0 plus times 0 minus, which gives a 0 minus, 0 minus times 0 plus, which gives another 0 minus, and 0 minus times 0 minus, which gives another 0 plus. So our result is 0 plus minus. One last product before we move on. 0 plus times the constant interval from negative 1 to 1. Here are the slices of 0 plus and the interval negative 1, 1. We have arbitrarily small positive numbers multiplied by 1, arbitrarily small positive numbers multiplied by -1, numbers close to 1/2 multiplied by 1, and numbers close to 1/2 multiplied by -1. We also have 0 itself as anything times 0. And we get everything in between. As 0 plus squeezes, this squeezes closer and closer to 0, so we see our result of 0 plus minus dot. Again, these just show important examples as practice. It's not necessary to memorize these results, as they can be thought through from scratch on demand. Any other near number product can be thought through in a similar manner. Coming to division, the best thing to do is reciprocate the second factor and multiply. Let's go through a few examples to illustrate. First, a simple one, 6 plus divided by 2 minus. If we replace division by 2 minus by multiplication by its reciprocal, 1/2 plus. The product then works out as usual, giving us 3 plus. We can divide 100 plus by positive infinity. We just replace division by positive infinity with multiplication by 0 plus, and we find a result of 0 plus. Division by the number 0 is simply undefined, as 0 has no reciprocal. But we could divide 0.01 plus minus dot by 0 plus easily. If we replace division by 0 plus with multiplication by positive infinity, and we see a result of positive infinity. Finally, what about star forms for division? These come when we multiply 0 plus and positive infinity. Depending on which one we reciprocate and move to the denominator, this gives us two basic star forms for division, 0 plus over 0 plus, and positive infinity over positive infinity. Note that positive infinity over 0 plus fits into positive infinity, and 0 plus over positive infinity fits into 0 plus, so these aren't star forms. Let's carefully work through just one of these, which are both 0 plus times positive infinity in hiding. Here are the slices of positive infinity for us to divide. We get smaller quotients when we divide a small number on top, such as 2, by arbitrarily large numbers on the bottom, giving us positive quotients arbitrarily close to 0. We get larger quotients when we divide arbitrarily large numbers on top by a small number on the bottom, such as 2, giving us arbitrarily large positive quotients. As usual, we also get all the numbers in between, yielding all positive numbers as quotients. What happens when we squeeze? Absolutely nothing. So our result is simply the constant interval 0 infinity. Exactly the same thing happens for our other star quotient, 0 plus divided by 0 plus. The signs in these forms could be any of plus, minus, and or plus minus, just with multiplication. With that, we close our introduction to multiplication and division of near numbers. Our next video will briefly review and connect all of our star forms. We'll finish this video series by discussing expressions and limits, then formal proofs. Please share this video and check our blog, where we'll announce new videos and discuss questions that come in. And don't hesitate to use the contact email below if you have any questions along the way.